What specific problem does your study address regarding language models and their generalization abilities?
This study addresses the problem of how data characteristics influence the generalization abilities of language models, LMs, particularly in the context of learning hierarchical grammatical rules versus relying on surface-level heuristics. We investigate the impact of training data composition, specifically the presence of center-embedded sentences, on a model's ability to generalize to out-of-distribution OOD data that requires hierarchical understanding. Our findings reveal that models trained on ambiguous data struggle to stabilize their OOD performance due to competition between different generalization rules, leading to inconsistent outcomes across random seeds. We demonstrate that only models that commit to a specific rule, either hierarchical or linear, exhibit stable OOD performance, highlighting the critical role of data diversity and complexity in shaping these generalization behaviors. Ultimately, our work emphasizes that the structure and diversity of training data are pivotal in enabling LMs to transition from simple memorization to robust generalization of complex grammatical patterns.
How does the proposed method or algorithm work? Illustrate step by step how you investigate the influence of data characteristics on generalization rules in language models.
The proposed method investigates the influence of data characteristics on generalization rules in language models, LMs, through a systematic approach involving two main tasks: question formation, QF, and tense inflection, TI. First, we train models on ambiguous data that allows for both surface-level linear rules and hierarchical rules, ensuring that the training data includes center-embedded sentences, which are crucial for inducing hierarchical generalization. Next, we evaluate the models on out-of-distribution OOD data that only aligns with the hierarchical rule, allowing us to measure their generalization performance. We analyze the stability of OOD performance across different random seeds, linking stable performance to the model's commitment to either the hierarchical or linear rule. Finally, we assess the impact of data complexity and diversity on training dynamics, identifying regimes where data diversity promotes rule commitment and generalization, while insufficient diversity leads to memorization without rule learning.
Can you provide a detailed example of how center-embedded sentences influence a model's ability to generalize hierarchically versus using surface-level heuristics? Walk through a specific example from your experiments.
In our experiments, we demonstrated that center-embedded sentences significantly influence a model's ability to generalize hierarchically rather than relying on surface-level heuristics. For instance, in the tense inflection task, we trained models on data that included both right-branching and center-embedded sentences. When the training data was dominated by right-branching sentences, the model struggled to learn the hierarchical rule, resulting in low out-of-distribution OOD generalization accuracy. However, when we increase the proportion of center-embedded sentences, which introduce recursive structures, the model began to favor the hierarchical rule, even when tested on right-branching sentences. This shift was evident as the model's OOD accuracy improved, indicating that exposure to center embeddings effectively directed the model towards applying hierarchical grammar rules, showcasing the critical role of such complex structures in enhancing generalization capabilities.
What are the theoretical or practical advantages of focusing on data complexity and diversity in your approach, compared to traditional methods of evaluating language models?
Focusing on data complexity and diversity offers significant theoretical and practical advantages in evaluating language models, LMs, compared to traditional methods. Theoretically, our approach reveals that the composition of training data, particularly the presence of center-embedded sentences, drives LMs to favor hierarchical syntactic representations over surface-level n-gram heuristics, which is crucial for achieving out-of-distribution OOD generalization. Practically, we demonstrate that models stabilize in their OOD performance only when they commit to a specific generalization rule, which is influenced by the diversity of the training data. This contrasts with traditional evaluations that may overlook the impact of data characteristics on model behavior. Our findings indicate that insufficiently diverse data can lead to memorization rather than rule learning, highlighting a critical pathway for improving model training and evaluation. Additionally, we identified distinct training dynamics regimes based on data complexity and diversity, providing a nuanced understanding of how these factors influence model performance across different random seeds. Overall, our approach emphasizes the importance of data characteristics in shaping the generalization capabilities of LMs, offering a more comprehensive framework for evaluating their performance.
How did you validate the effectiveness of your proposed method? What experimental design and metrics were utilized to assess the model's performance on OOD data?
To validate the effectiveness of our proposed method, we employed two tasks: question formation (QF) and tense inflection (TI), using synthetic datasets that included both ambiguous training samples and unambiguous out-of-distribution OOD samples. The model's performance was assessed based on its accuracy on the OOD data, which was designed to only be compatible with the hierarchical rule, thereby allowing us to measure hierarchical generalization. We varied the composition of the training data, specifically the proportion of center-embedded versus right-branching sentences, to observe how these changes influence the model's ability to generalize hierarchically. Additionally, we tracked the stability of OOD performance across different random seeds, noting that stable models consistently committed to either the hierarchical or linear rule, which was quantified using total variation metrics. This experimental design allowed us to draw clear connections between data composition, rule commitment, and OOD generalization performance.
What were the key results obtained in your experiments regarding the relationship between training data composition and hierarchical generalization performance? Can you summarize the insights gained from your findings?
The key results from our experiments indicate that the composition of training data significantly influences a model's ability to achieve hierarchical generalization. Specifically, we found that training on center-embedded sentences, which introduce recursive structures, drives models to favor hierarchical syntactic representations over surface-level n-gram heuristics, leading to improved out-of-distribution OOD performance. In contrast, when training data is dominated by right-branching sentences, models struggle to generalize hierarchically, often resulting in low OOD accuracy. Additionally, we observed that models only stabilize in their OOD performance when they commit to either a hierarchical or linear rule, with heterogeneous data leading to instability due to competition between these rules. Overall, our findings underscore the importance of data diversity and complexity in shaping generalization behaviors, revealing that a balanced mix of hierarchical-inducing and linearity-inducing examples is crucial for effective rule learning.